This is the Chem 1 lesson over the last two types of chemical reactions, single replacement and double replacement. So single replacement reactions are where you start off with an element and a compound, and they're going to rearrange, and one of the elements is going to be replaced by the single element in the reaction. So if you look at this picture, we've got a single element A and we've got a compound BC. Element A is going to be able to cut in and create a compound with C, and then element B is going to be by itself. So you're going to start off with an element and a compound, and you're going to end up with an element and a compound. So in this case, if A were a metal, it would go in and try to replace B, so then B would be by itself, and we'd now have a compound with A and C. So if we had the compound of copper 2 nitrate and iron, iron is going to then try to replace the metal copper and replace that guy out. So then you end up with copper by itself, and you end up with a compound of iron and nitrate. Then we're going to have to balance this guy out by putting a 3 in front of our copper and our 2 in front of our iron 3 nitrate. So as you can see, one active element is going to take the place of another less active element in a compound. So on the back of your periodic tables, you have something called the activity series, which tells you the exact reactivities of your metals and your nonmetals. So one element can only replace a similar element if that element is below an activity series. So my analogy I always talk about is like, for example, if you were at a school dance, and this girl was dancing with maybe a kind of a geeky guy, maybe like an Urkel, right, of school, and the captain of the football team asked to cut in. Is she going to choose the dorky boy? Is she going to go with like the hunky football player? Well, again, if we're following kind of social norms, whatever, she's going to choose the more attractive boy, the football player, and replace that. So the idea of the example we had with copper and iron, so iron was trying to replace copper. If you look at them on your list, so let's see, iron and copper. Find these guys on our list. Iron, and we have copper. So we can see that iron is able to replace copper since it's higher up, right? Iron's the more reactive metal. It's able to beat out copper in that reaction. You have to worry about those elements that have more than one possible charge. Same thing, so with iron, we didn't know the charge on it. We had to look up on our list. Iron can be +2 or +3. +3 is circled, so that's going to be the one we choose. Same in UDA here. So we've got some examples. So you can recognize all of these because they're going to start off with an element and compound. So in this case, I've got magnesium and hydrochloric acid. So hydro in the front tells me that my anion is just an element. H is +1, Cl is -1, so they're going to be in a 1-to-1 ratio. And before we move forward, you have to check your activity series because you have to make sure that magnesium is more reactive than whatever it's going to try to replace. Since magnesium's a metal, it's going to try to replace the metal in hydrochloric acid, which is kind of a trick because there is no metal. But we do have hydrogen that behaves as a metal. If you actually look at your activity series of metals, hydrogen is actually listed on there because it actually behaves like a metal. If you check it out, magnesium is higher up than hydrogen. So the reaction is going to happen. So then we're going to form a compound with magnesium and chlorine. So magnesium's +2, Cl's -1, so we're going to end up with MgCl2. And then hydrogen's going to be by itself, and it's a diatomic. So finish out that word equation. We're going to get magnesium chloride and hydrogen. And we've got to balance out that equation. So our magnesiums are balanced, but our chlorines aren't. So I put a 2 in front of my HCl, which balances out the hydrogens. So the next one, we've got potassium and aluminum chloride. So let's see, aluminum is +3 and Cl's -1, so we're going to get AlCl3. And so now you have to ask yourself, can potassium replace aluminum? Now, since potassium is a metal, it's going to go after the aluminum since that's the metal. If you check your activity series, potassium is way high up there. It's a third on the list, so it's very reactive. It's very attractive, right? Hunky, think about that football player. So it is going to try to make that replacement. So it means we're going to have a compound formed with potassium and chlorine, plus and minus 1, and then poor aluminum is going to be stuck by itself. To balance this guy out, maybe we want to do that next. We would put a 3 in front of our KCl, which means we'd have to put a 3 in front of our K. Don't forget to go back and finish your word equation. We're going to end up with potassium chloride and aluminum. So our next one, I've got bromine plus silver fluoride. So bromine, diatomic, don't forget about those guys, and silver fluoride. So silver is Ag, it's +1, fluorine's -1, so we're in a 1-to-1 ratio. Now this one, our single element is bromine and it's a nonmetal. So it's actually going to try to replace fluorine since it's non-metal. So you do have to check your activity series. Is bromine more reactive than fluorine? If you look at it, fluorine's actually, well, we know, that's the most reactive nonmetal. So this reaction is not going to be able to happen. Nothing would happen if you mix these two things together. Bromine would not be able to replace fluorine, so no chemical reaction would happen. You can write out the words no reaction, or you can just abbreviate that in R. Now the next one, we've got calcium. That's a metal, so it's going to try to replace the metal in magnesium oxide. So double check your activity series. Can calcium replace magnesium? Barely, right? Calcium is just one above, but that reaction will happen. So draw ourselves an arrow. So we're going to have calcium oxide and then magnesium by itself. And this guy's already balanced. I'm going to have one of everything, so that one's pretty easy to balance. Finish our word equation by saying calcium oxide and magnesium. And last one, copper 2 nitrate and hydrogen. So copper 2 nitrate, copper nitrate with a 2 after it, plus hydrogen. So now hydrogen is going to be our singular element. What's it going to try to replace? It's going to try to replace copper. So check your activity series and make sure that's going to happen. Hydrogen is higher, so which means we're going to end up with hydrogen and nitrate. Oh, so we're going to make an acid here, and copper by itself. So balancing this guy, let's see, we are going to need to have 2 in front of my acid. I think that's it. Yeah, okay. So let's finish our word equation. HNO3, okay, so we got an acid. NO3 is nitrate, so it's going to become nitric acid. And copper. Our last type of chemical reaction is going to be our double replacement. So you can see it's a really big party here, but if you want to break it down, we're going to end up with a compound and another compound, and we're going to end up with 2 compounds in the products, but if you notice what happened is that the A and the C, they swapped places. So we've got a lot going on here. There's a lot of different pieces to these guys, but you're going to have an element and a compound, and you're going to end up with an element and a compound. So in this case, we could, if A and C switched places, you'd have a compound made of C and B, and you'd have another compound made of A and D. So if our compounds were, let's see, aluminum, nitrate, and magnesium sulfate, the aluminum and the magnesium can just swap places. So you'd end up with magnesium and nitrate plus aluminum and sulfate. And then we need to balance them. So we're going to need to put a 3 in front of our magnesium. So when you do double replacement reactions, you want to be sure that the 2 positive ions switch places so that the compounds you get in the end are still made of a positive and a negative. So you can actually switch either both positives or both negatives, but don't make compounds out of 2 negatives or 2 positives. There is a special case you need to know. It's where you have an acid, any acid, and a carbonate. Now, what actually ends up happening is the H and the whatever from the carbonate are going to form a salt. But then the other thing you're going to get is actually carbonic acid, H2CO3, which is not stable. Carbonic acid actually naturally breaks apart into water and carbon dioxide. So you actually don't write it out like that. You just write out the fact that you're actually going to get three things. It is a weird case, so you probably want to notify that in your notes. And the last one is not a special case, it's just a specific example, is a neutralization. We'll talk a lot more about neutralization when we talk about acids and bases. But when you mix an acid and a base together, they do neutralize each other and they form a salt. Remember, that means any salt, any ionic compound, and water. So, sodium chloride and sulfuric acid. So I've got sodium chloride and sulfuric acid. So if it is ic, we know it's 8. So it's going to be sulfate, H2SO4. So now we need to swap. I usually just swap the positive things because they're listed first. So we're going to end up with H and Cl. And then we're going to end up with Na and SO4. Na is +1, but SO4 is -2. So we're going to end up with Na2SO4. And let's see, we need to finish the word equation. HCl is hydrochloric acid. And then we're going to have sodium sulfate. And balancing. Let's see, Na, we're going to need 2 over here. We're going to need 2 in front of our HCl, 2 hydrogens, 2 chlorines. Okay, we got it balanced out. Now the next one, iron 2 chloride. So iron is 2. Oh, I forgot. Leave space to balance that guy. FeCl2 plus sodium phosphate. Sodium's +1, but phosphate's -3. Arrow. So the Fe and the Na are going to swap, so that means we're going to end up with sodium and chlorine together. It's going to be a 1-to-1 ratio. And then we're going to have iron. Remember, iron's +2. We know that based on how it was on the reactant side. And phosphate, which is -3, so we're going to end up with Fe3PO4 2. So balance and finish the word equation for this guy. Okay, so we're going to need, there we go, and finish our word equation. Sodium chloride and iron, this iron was 2 phosphate. Next one, aluminum phosphate. Aluminum is +3, phosphate is -3, so one of each of them, plus nickel 2 sulfide, so nickel is +2. Oh, sulfur is -2, arrow. So now aluminum and nickel are going to swap places. So we're going to end up with nickel and phosphate together. Nickel's +2 and phosphate's -3. So we're going to Ni3PO4 2. Plus, let's see, we're going to have aluminum and sulfur together, Al2S3. And balance it and finish the word equation. So this is a situation where I think about PO4 as a polyatomic because it's on both sides. I would probably start off by putting a 2 in front of my aluminum phosphate and then a 3 in front of my nickel 2 sulfide, and that balanced it out. Now it's just a matter of finishing that word equation. Nickel 2 phosphate and aluminum sulfide. Good. Next one, I've got sodium hydroxide and sulfuric acid. So sodium hydroxide, NaOH, +1 or -1. Sulfuric acid, ic is 8, so it's going to be sulfate, H2SO4, arrow. So now the sodium and the hydrogen are going to swap places. So we're going to end up with hydrogen and hydroxide, HOH, which is water. You're more than welcome to write that as water if you want. And then we're going to end up with sodium and sulfate. So balance this guy out. This is one of those times where you might want to think about water as HOH since we have an OH on the reactant side. To put a 2 in front of our sodium hydroxide and a 2 in front of our water should balance that guy out. Now what we need to do is finish the word equation. We're going to have water, and sodium sulfate. And we've got one more down there on the bottom. So I've got hydrochloric acid and magnesium carbonate. So I've got hydrochloric acid, hydro means it's just chloride, and magnesium carbonate. Okay, alarm should be going off here. We've got an acid and a carbonate. So one of the things we're going to get is going to be a salt. Remember, salt is anything that's made up of positive and negative. If we swap magnesium and hydrogen, that salt's going to be magnesium chloride. Now that means our other thing is going to be hydrogen and carbonate. That's carbonic acid, but remember, carbonic acid is not stable. It automatically breaks apart into water and carbon dioxide. So when we write this, we're not going to write carbonic acid. We're going to write out water and carbon dioxide. So we can go ahead and balance this guy. Put a 2 in front of our HCl. See, that gives me 3 oxygens, 3 oxygens. Oh, I think that's balanced. So now it's just a matter of finishing that word equation. I've got magnesium chloride. There's water and carbon dioxide. So that's our chemical reaction. So single replacement in an element in a compound, so that element is going to replace its like element in the compound. So if it's a metal, it's going to replace a metal. If it's a non-metal, it's going to try to replace a non-metal. Do check your activity series to make sure it's going to happen. It does have to be more reactive in order for it to happen. And then a double replacement where you have 2 compounds and you end with 2 compounds. You need to either swap both positives or both negatives. So you end up with 2 new compounds that are made up of positive and negative ions.